Hey everybody, welcome to AP Biology Chemistry Review video number 2. In this video, we're going to talk about how molecules and compounds are created based on bonding, and then we're also going to look at different types of chemical reactions. So let's jump right in. So to start with, how do atoms bond? Let me make sure that this is nice and straight for you. If you remember in the last video, we talked a little bit about valence electrons. And the valence electrons are those electrons that are found in the outermost shell. So that's an important term right here, valence electrons. And based on the number of valence electrons that are not paired, along with the octet rule, don't forget about that octet rule, where the valence shell wants 8 electrons for the most part. There are a few exceptions. That's going to create the bonding. Now there's 2 ways that bonding can occur. In an ionic bond, what will happen is atoms will either lose or gain electrons in order to create that octet rule, that stable outer shell. And when they do that, those create ions. Remember, we talked about what happens when you change the number of electrons in an atom. You create a charged atom. So if I do that, I might end up with one atom that is positive because it lost electrons, and I'm going to end up with an atom that gains electrons, so that one's going to be negative. That attraction between the two creates a bond, and we call that an ionic bond. Now, these kind of bonds are always going to be between metals and nonmetals. So if you look at the periodic table, just to kind of give you a review of the periodic table, if there's like that stair step that kind of shoots through it, everything on this side is a metal, everything on this side is a nonmetal, and the things kind of along the stair steps are what we call metalloids. So this is going to be between a metal and a nonmetal. The metal is going to lose electrons and become positive. The nonmetal will gain the electrons and become negative, and then that attraction occurs between the two of them. On the other hand, we have a different type of bonding. We have something called a covalent bond. I want you to think about the words. Ion is in this one, so it's between ions. Co means to share. Okay, so that prefix means to share or together. So in this case, what's going to happen is they're going to share electrons in order to fill their octet. Now this is going to happen between nonmetals and nonmetals. So for example, carbon dioxide is an example in which the electrons are going to be shared. So those are the 2 types of bonds that atoms can make. There's a third type, which is called a metallic bond, but we're not going to spend our time on that. So the question becomes, how do you know what type of bond will form between 2 elements? The first thing you can do is you can ask this question right here. Is there a metal? If there is a metal, okay, it's going to be ionic. Like I said, there's that third type, the metallic bond, but that's pretty rare. So if there's a metal, it is probably an ionic bond. If not, then it is going to be covalent. So like I said, that's the first step you can do. Another thing you can do is look at what's called electronegativity. So here's another vocab word. This is an important chemical or physical property of atoms. Basically, what electronegativity is how strongly that element pulls electrons to it. So for example, oxygen and fluorine and chlorine, those are very strongly electronegative. So the electrons really want to be around those elements. So they have high electronegativity, okay? Versus something like, I'm trying to think, carbon, for example, has pretty low electronegativity. So what we can do is we can look at the difference in electronegativity between the atoms. So if I look between, let's say, hydrogen and oxygen, there's a pretty big electronegativity difference. And I'm not expecting you to know the differences. I'm not expecting you to be able to identify that. You just have to know that this is one way we do it. And then the bigger the difference, the more polar it becomes. And eventually the difference is big enough if there's a metal in there that it becomes an ionic bond. So electronegativity is going to be a very important concept, especially when we get into water and hydrogen bonding. Okay, so let's talk about that. Let's talk about what makes a bond. So now we're talking only about covalent. This is only in covalent bonds, okay? Ionic bonds are always polar. They are very strongly polar because of the ions. They're actually, I shouldn't say that. Let me rephrase that. They are neutral. However, when they are dissolved, you get your ions back. But let's talk about covalent bonds. And covalent bonds can either be nonpolar or polar. Now I want you to think about the word pole. And I want you to picture the earth and think about what the earth looks like. Okay, so here's the earth. I'll put some water on there. Boo, doo, 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 doo. Here's the oceans. The Pacific Ocean's pretty big. Okay, and on the earth we have a north pole and we have a south pole. And it's very similar to that. But in the case of chemistry, we have a negative pole and we have a positive pole. Okay. Now that's not saying that those poles are always going to be that way, but it's basically saying there is a part of the molecule in which one side of it tends to be more negative and one side tends to be more positive. So how does that come about? So let's talk about that. Now in a nonpolar covalent bond, oops, got the wrong kind of pen there. In a nonpolar covalent bond, remember we talked about covalent bonds as being sharing electrons, okay? And in a nonpolar covalent bond, they're shared equally. So let's look at this, this molecule of Cl2. Notice that chlorine is here and they're sharing these 2 electrons in the center. So they have, their octet rules are filled. You can go 1, 2, 3, 4 times 2 is 8. 1, 2, 3, 4 times 2 is 8. So both chlorines have 8 electrons around their valence shell. Now, notice that they are sharing these electrons and they're sharing them equally because the electronegativity difference between the 2 chlorines is 0. So there's not one that is pulling it stronger one way or another. Now let's look at a polar covalent bond in which they share unequally. So we have hydrogen and we have chlorine. Now hydrogen and chlorine are sharing valence electrons. So they have this one shared bond between them. However, chlorine is very strongly electronegative. And so I want you to think if you were to draw these electrons, spending time around these atoms, they share them, but picture this being the electron, like kind of spinning around these. They're going to spend way more time around the chlorine. And because of that, that creates what we call a partial pole. And we use the Greek letter sigma to indicate partial. So this molecule has a partial negative side on the right where the chlorine is. I shouldn't say the right because this is a 3-dimensional model. And it has a partial positive side on the left. Again, I shouldn't say right or left, but on the hydrogen side. And so because of this unequal sharing of the electrons, we have what we call a polar covalent bond. Hang on to the idea of polar covalent bonds because we're going to come back to that when we talk about the polarity of water. But I want to talk a little bit about a very important big idea in biology, and that is that form follows function. So the function of the molecule is what is basically going to determine its form. And I have a couple examples here to show you what I'm talking about. You guys might remember this molecule from biology. Your freshman biology. So this is a phospholipid. If you remember, this is what makes up your cellular membrane. So you have a phosphate head, and then you have 2 fatty acid tails. Okay. Now, if you remember from your biology, this shape is very important, and because of the function of that phospholipid bilayer, that is what has evolved into this shape. Here's another example of shape being really important. This is actually an antibody. So let's say that you are exposed to the flu and your body is fighting off the flu. It's going to create this antibody here. And it actually, if you were to look at the protein, it really is kind of shaped like a Y, like this, the way it folds. And these top parts of it, let me put a different color on there so you can see what I'm doing. This part of it here, where you see like this and this, so this is what we call the antigen binding site. And every virus and bacteria, anything that's not made by you also, but you have foreign antigens that enter your body. And so your body is going to build this antibody that will be against specific antigens. And so it has to have a very specific shape. So maybe this A is to fight the flu. Maybe C is to fight COVID, right? Notice COVID is not going to fit into that antibody. So if you haven't been exposed to COVID, you don't have the antibody to fight it. Now, once you've been exposed to it, you will. So that's important. That's a good thing. Not necessarily getting COVID, but having the antibody. Here we have a receptor. So if you remember, this is our phospholipid bilayer. This would be like the cell membrane. And here we have a receptor. Now these receptors have this chemical shape, and that shape is very important because it is very specific to a specific messenger. So for example, if my cell wanted to be, let's say that this was a receptor for insulin, okay? The shape of it is only going to respond to insulin, which is good. You don't want it responding to anything else. And that's why shape is so important. All right, so let's talk a little bit about energy and chemical reactions. We're going to go into this in a lot more detail when we go into enzymes. Enzymes is a big part of this class, but I just want to briefly remind you about this graph. Okay, so here on this side, we have how much energy there is found in the whatever we're looking at, and over here is time on the x-axis. So my reactants, if you notice, start with a higher amount of energy than my products, all right? And we basically are gonna have something happen in between. I like to call it the magic of biology. And this has to be exothermic, because if you think about it, if my products have less energy, that means I had to get rid of or release energy. Now, if I have, so we call that exothermic. Exothermic reactions are those that release energy. Now, I can also have an endothermic reaction, but in that case, it's actually going to be where my products have a higher amount of energy than my reactants. Now, what's interesting is in our bodies, this little bit, this little mountain here, this little hill that you see is very important. And we're going to talk a lot about this in the future. So if you don't understand it, it's okay. We're going to talk about it some more. But this is called activation energy. And there's a certain amount of energy that is required for reactions to occur. They just can't even get started without a little bit of energy. And in our bodies, we have so many reactions. All of them require enzymes in order to do that. Otherwise, we'd have to wait around for so long, we would actually die. But we'll talk more about that when we get into enzymes. So what are the two types of reactions in the body? This should say reactions, not energy. Sorry about that. There are two types, and I have some pictures here to help you remember. The first type of reaction is called an anabolic reaction. In that case, you're taking lots of little pieces. So let's call this piece A, B, C, and D. And we add some energy. Okay, so anabolic reactions are endothermic. And we create a new, bigger molecule that we'll call E. So I want you to picture someone who's injecting anabolic steroids. That's where that term comes from. Anabolic steroids are used by bodybuilders to build muscles. Okay, so anabolic builds larger molecules. Now, on the other hand, you can also have something called a catabolic reaction. In this one, we're breaking a larger molecule down. So here's our big molecule E, and we're going to break it down into A, B, C, and D. And it also releases energy, so this is going to be exothermic. Now, I think of this as if you picture a cat knocking something off of a counter, it's going to break into little pieces. So I always picture, like, imagine you built the Death Star out of Legos, right? It took you like 500 hours to build it. And the cat knocks it off because it's catabolic, and it breaks off into all its little pieces of Legos. So that's a good way to remember it. And remember that you release energy in order to break something down. So this would be like digestion. And then you have to add energy in order to build something like muscles. Okay, last slide. We're just going to remind ourselves how to read a chemical reaction. Real quick, you guys should be pretty good at this after having taken chemistry. Reactants are on the left side of the arrow. Products are on the right side of the arrow, okay? The prefix, which is this number here, applies to the whole molecule. So I have 6 CO2 molecules. I have 6 water molecules. It's not saying that I have 6 carbons. But then when you look at the subscript, so here, if you see the 12, that means on this molecule, I have 12 hydrogen in that molecule. If I have something in parentheses, let's say I have CO2 and I have 4 of them, that 4 needs to be multiplied to each thing. So then I would have C4O, what would that be, 8. It's kind of a weird way to think about it because that's not what you would have. You would actually have 4 CO2 molecules, but when you look at how many of each thing you have 4 of these and 8 of these. Now, it's important also to note something called, it's the law of conservation of mass. Because of the conservation of mass, this is a law, a physical law, the numbers of each element on the reactant side must match the number of elements on the product side. This is why we balance equations. Okay, you cannot make matter. Matter is just going to be changed, but the number you have on the left has to match the number you have on the right. So if you notice, let's say we look at CO2, I have 6 C's here, I have 6 C's here. I have 12 H's, 6 times 2 is 12, so that's good, so on and so forth. So you balance the equation in order to make sure that you are conserving your mass. And that's it for this video. Thanks, guys. Have a fantastic evening.